go through this. And that's because of the quiz. We now have kind of a half a class to kind of get through these calculations, but I do want to get through them. What I normally do is I normally take the time to show you some equipment, but I will have a chance to show you some of the equipment in a little more detail a little later on. But sometimes I take the time here to show you some equipment that we use when we prepare solutions. But again, because of the time left in class, I just want to get through the calculations, and I'll briefly mention the equipment. And then at a later time when we are getting ready to use the equipment, I'll go through the equipment explanation. So in today's lesson, we want to talk about how we actually prepare solutions in the laboratory and some of the equipment that we use. And when we make a solution for an experiment, we can either create it one of two different methods. And one method starts from a solid that we weigh on a scale and then dissolve that in a certain given amount of water to create a solution. And the second is a dilution of an already existing solution, all right? Many of our chemicals come as solids, so in creating a solution, we can weigh out a certain mass of solid, dissolve that up, put it into a measuring container where we can know the volume very well, and we can create that solution. But some of our reactants, an example of that is hydrochloric acid. Hydrogen chloride is a gas, and it's a very, very dangerous gas in that if you were to inhale hydrogen chloride gas, it would dissolve in the moisture of the interior of your lungs, where it would soon dissolve and become a very strong hydrochloric acid, and it would burn the inside of your lungs, and then it would cause oozing and that type of thing, because you've now got a burn on the interior of your lungs, and you would essentially suffocate to death as moisture enters your lungs, and you would die. So you don't want to inhale hydrogen chloride gas. But hydrogen chloride dissolved in water, even at a very strong concentration, isn't dangerous because that hydrogen chloride dissolves so well. So when we get hydrogen chloride or hydrochloric acid, it comes in a stock solution, stock meaning that we put it in the stock cupboard in order to, create a weaker version of it. It comes in a stock solution that's 16 moles per liter. It can be dangerous, but I use it carefully in the fume hood, goggles, all that good stuff, and then I dilute it down to either 1 mole per liter or 0.5 moles per liter, which is what you guys typically see in the lab, all right? So we can either start from a solid or we dilute an already existing solution. So first let's define a few things, and then we'll do a calculation or two. So the first little definition there says standard solution, a solution made by dissolving a precise mass of solid in a precise volume of water to get a precise concentration. It's always easier to have good precision, and when I say precision, I really mean significant digits. When I say a precise concentration, I mean a concentration that has a lot of significant digits that's been measured very precisely and then calculated with that same number of significant digits. And if we start from a mass, we can obtain a scale, and our scales have 2 decimals, and if we weigh out something like 10 grams, point something something, that gives us 4 significant digits on the mass. And that's fairly precise. Now, in order to maintain that precision in our calculation, we need a precise way of measuring volume. If I were to measure volume in terms of creating a solution in, say, something like a beaker, then I wouldn't have a very precise volume, because even if I attempted to measure out exactly 80 milliliters, say I'm using this, due to the large area of the cylinder when it comes to a beaker, if I were to miss that mark by any little amount, because the area of the cylinder is so large, I would be off of my 80 milliliters by a significant amount, all right? So if you've got a really wide container like a beaker, it's not good for getting precision volume measurements, all right? Because if you remember back to your, what is it, grade 8 or 9 geometry, when you talk about the volume of a regular solid, you talk about the area times, however tall it is. And if the area is big, every little error in your height is going to create a large error in your volume. So a beaker would not be a good container to measure out a precise amount of water. A graduated cylinder is better because it then has a smaller area and it is taller, so that you can get on that mark better. And if you make a little mistake on that height, then it's not as big of an error involved. What you can see there on the screen, and what I have here, is what's called a volumetric flask. And these are designed to be very, very precise when it comes to measurements. It doesn't have a whole lot of graduations on it. It actually has exactly one graduation mark there. I don't know if you guys can see that little ring there. Can you see the ring? See the little ring there, right? There's a little graduation mark there, and if I fill it to where the bottom of the meniscus is right on that line, then I know I have exactly 500 milliliters. Actually, it's better than that. It goes to 1 decimal. It's 500.0 milliliters exactly if I do my measurement on the meniscus properly. So using a volumetric flask is one way of getting a very accurate volume measurement, all right? And that little link there would have linked us to a little video that shows us how we should use a volumetric flask. But because I want to get to the end of the calculations, I'll show those later on in the week when I get some time. I want to make sure I get through the calculations today. All right. So a standard, one last thing. I say that a standard solution is only created by a solid. We can use a standard solution to react it with another solution that might be unknown, and we can figure out the concentration using a technique. And we're going to do that technique next week. It's called a titration. But when you use a standard solution up against an unknown solution, if you do it properly, you can now say that you've standardized that other solution. So then you've made it a very, again, precise concentration measurement. So even though you've created a solution that's not from a solid, maybe from dilution, you can still standardize it up against something you know very well. You just have to know one of the concentrations very well. So even though in my note it says it comes from a solid, you can standardize other solutions and get their concentration to be known very precisely. Okay. Now this particular page, all I want you to write down is the box there. But this particular page simply has instructions on how you would make a proper solution. And this is kind of what we would have seen in the video. And again, I'll show it later on. But, calculate the mass of what you need to make. And I'm just going to go through the steps very quickly, because this is more of something you might see in a multiple choice question where I ask you, is this a proper procedure, or which steps we're missing, or something like this. This is something you read over a couple of times, and then you've got it. Obtain that particular mass on a scale, all right? Put it in a 150 milliliter beaker. Dissolve the solid in 40 to 50 milliliters of pure water in the beaker. Better to swirl than it is to stir, right? Because we know if we stir with a stirring rod, we'll lose some of it. So swirl it and dissolve it. Transfer the solution into a volumetric flask. In this case, it says 100 milliliters. So pour that solution in. It says also rinse the beaker 2 to 3 times. So you'll rinse that beaker and put it in the volumetric flask so that you don't leave anything out of the beaker. Then you add your water until you get to the graduation mark. Once you have it at the graduation mark, you can You can invert it and agitate it to make sure that it's dissolved. And once you've got it inverted and agitated, you've successfully made your standard solution. All right. So that's just, again, a bit of information on how you would do it. And again, there's a link to that, that would bring it to my video that I have on my hard drive. It doesn't matter. Okay, let's continue on, though. Let's do a few calculations here. And the calculations here are actually no different than the calculations that you did even on your quiz. They're molar calculations. The only difference is the number of significant digits. When I say that it's in a 250 milliliter volumetric flask, I'm implying 4 significant digits, 250.0 milliliters. Other than that, your calculation is the same. So this is very much a review of yesterday's stuff. So if you weren't here yesterday, this is a good, this is a good look at what we did yesterday. I'm going to attempt to do it with our little device here so it can be on our little movie. So just like yesterday, the question asks, what concentration would be obtained? What's the first thing I write? C equals N over V. So I'm looking for that C equals N over V. And then I go looking for that stuff. Is there anything out there that I can already put in my equation? Yeah. Yeah, I can put in that 0.25, and I'm actually going to put 0, because it's in a volumetric flask, we know that we have 4 significant digits there, liters. And again, we know how my horizontal lines are. Woo! I apologize. That was horrendous. What's my next step? How am I going to figure out this concentration? Jess? Yeah, so I got to convert the grams of sodium chloride to moles of sodium chloride using the molar mass. So the calculations, like I said, are the same as yesterday. Sodium chloride is one we see quite a bit in our questions. What is that, 58.5? Yeah. 58.5 grams per mole, 8.75 grams. .5 grams at the bottom, 1 mole on the top. Again, don't clear your calculator. You actually don't even have to stop there. You can have your numbers in there and then just press divided by 0.250. I do like you to write it down, because then if I give you 4 marks for something like this, 2 for the first calculation, 2 for the second calculation, I can see that you've done all the steps. Does somebody have the number for the moles there? Yeah, TJ, what do you got? 1495. Those are plenty significant digits, which is excellent. That's moles. 0.1. We don't like it? Is it good? 495. That's moles. Now, in the end, we are limited by our 3 significant digits in our molar mass. We could have actually taken an extra digit. We could have taken more digits on that periodic table and had a better calculation. But don't worry about it. We've done it to the best of what I've told you to do. 1 decimal for your molar masses. What do we have for a number? TJ, what's your number there? 0.598 to 3 significant digits. And that's moles per liter. Any questions or concerns? Same questions as yesterday, nothing new. Let's do one more where we are, we're maybe looking at this a little more logically. This is a little more like the question that I would have to sit down and do in order to prepare a solution for you guys for the class. Let's say I come across a new lab, and the lab tells me that you're going to need some copper sulfate, and it has to be 0.550 moles per liter for the students, and they're going to need so much of it, so you need to make a liter of it. And if I get that type of situation, I have to sit down and do this type of question to determine how much solid I have to put on the scale. So this is a little more realistic in terms of what you would have to do in order to figure out what you need. Yep. You do have to include that, because if I go to then my stock room and I take my copper 2 sulfate, it will say copper 2 sulfate pentahydrate. That's the type that we purchase. So I do have to take that into account when getting the molar mass. That's correct. So in this case, and I know you guys are a fan of using equations. Many of you, even on this morning's quiz, and I saw you guys working out there, sometimes like to use that C equals N over V, right? And you might put in the V and you might put in the C and solve for N, the number of moles. You definitely can do that. And then you'll use those moles and the molar mass to figure out the mass. There's nothing wrong with that, all right? But the method that I've been teaching, if I start with liters and I want to get to moles, the conversion factor I need is the molarity, 0.550 moles per liter. And so I can use that as a conversion factor. But I do know that there's some of you out here that would go, all right, C equals N over V, and I need N, so I'm going to bring this V up here, C times V equals N, and I can get the moles just like that. And then use the molar mass to figure out what the mass is needed. I don't care what method you use to get your answers. To be honest, and I think I said this earlier on, when I was taught chemistry in grade 11 and 12, my teacher didn't use conversion factors whatsoever. It was equation after equation, and you just simply went through a bunch of little equations as you went. Whichever method you understand and makes sense to you, I don't care what you use. I'm going to continue on with the conversion factors because that's what we've been kind of doing all along, so I'm going to keep doing that. To go from moles to grams, I need a molar mass. I'm going to need a molar mass whichever method I use. That means I need copper 2 sulfate, pentahydrate, 5 H2Os. When I do a hydrate, I leave the waters together. I would just go 5 times 18. All right, don't break up the H's and the O's. We know that water is 18. Sulfur, 32.1, is it? 32.1, and copper, yeah, I don't know that one. 63.5? 63.5. Oh, and my horizontal lines are terrible. So we'll take a molar mass. When you get it, yeah, Jess? 249.6 grams per mole. Is that for everything? That's for the pentahydrate as well? Yeah, we're good. So again, because I like using the conversion factor method, well, you know what, I don't care which method you use. I don't have a preference. Because we've been using it, I write down what I have. But keep in mind, it's a volumetric flask. We know this volume very well, 4 significant digits. So as soon as it says volumetric flask, you can assume 4 significant digits. The molarity, for every 1 liter on the bottom, I need 0.550 moles. And the molar mass, I got to have moles on the bottom for every 1 mole. There is, what, 249.6 grams. And it's going to get it for me. We'll just divide the world here so we don't run into things. And just what do you got? 137.3 grams. And actually, again, we're handcuffed. Oh, no, we've got 4 significant digits there. Great. That's good. We'll leave it. Bang. Oh, actually, we're handcuffed by this guy. This is 3 significant digits on our particular concentration that we want. Doesn't matter. In actual fact, if I'm making this, I could make it to as many significant digits as I want. I could actually add a 0 there. We'll just leave that right there. Okay? So on my scale, I'd put 137.3 grams. I'd put that in a little beaker. I'd dissolve it up. I'd put it in my 1 liter volumetric flask, rinse it 2 or 3 times, get to the graduation mark, be done. I'd have my solution ready to go. Okay? So again, the calculations are the same as yesterday. All I'm saying is if we're dealing with a volumetric flask, you can assume 4 significant digits. All right. Let's now talk about what we deal with when, there are some questions that deal with making solutions from solids. And now I'm going to talk about making solutions when we dilute things. Okay, dilutions. You don't need a big fat arrow for the picture, but I would draw the picture in there. Don't worry about the colors as well. And don't worry about the notes on the videos. Again, I'll show them to you a little later on in the week. So in my little picture there, what I'm trying to kind of get across is that I have some highly concentrated solution in this little beaker. See, it's red, danger, concentrated. And I'm going to pour that into the big beaker, and then we're going to bring the volume up to something where I wanted to dilute it. Now, that wouldn't be a very precise way to dilute one beaker into the next beaker. This is just a quick little schematic to kind of illustrate that I'm adding some liquid to it. The way we would actually measure out the concentrated would be using a graduated cylinder or a type of apparatus here that's called a pipette. A pipette is essentially a glorified, expensive straw that you can draw the liquid up. It also has a little graduation mark, but then it allows you to know that you've got exactly 5, 10, 20, depending on what the pipette says or is built for, milliliters of your concentrated whatever. And again, I will go over in more detail how to use this. You measure out what your concentrated solution is. You put it into the volumetric flask. You let the liquid go in. You then dilute to the dilution mark, and you've created a fairly precise diluted solution. So the picture is just representing dilution. This is the way you would do it if you were wanting to be precise, and I will explain and tell you in more detail when you have to use those things. All right. But for this particular picture in particular, it's going to help us out here. So hopefully you've got a little beaker here, a nice little couple of rectangles. You just need a single arrow that you're going to dump it in there. It's not a big deal. But what I want to express are some numbers that we're going to have to be calculating. So if this is the concentrated one, we can say that we have V1 milliliters of that concentrated solution, some hypothetical volume. And that volume of that particular concentrated solution has a concentration of C1. The ones are just representing one of the solutions. And it doesn't have to be even the concentrated ones. You could have a dilute solution evaporate off some of the water and make it more concentrated. So this equation we'll use for diluting, or if you evaporate some liquid, how to calculate what the new concentrated version is. As long as we know that there are concentration numbers and dilute numbers. Whether we use ones or twos, it doesn't matter. Now, we know the equation C equals N over V. And if I'm talking about C1 and V1, just as I stated, that means I'm going to have an N1. I'm going to have a certain number of moles in that concentrated solution. And if I rearrange this equation by bringing this V1 up with the C1, then I'll have C1 times V1 equals N1. All right? And that N1 essentially means the moles in the solution. That's how many moles are in that concentrated solution. Now we're going to take that, we're going to dump it into the bigger beaker, and we're going to add some more water. And when we're done, we're going to have a V2. We're going to be at a new, larger volume. And because we've diluted it, we're now going to have a new concentration, a C2. And just like on this side, I can rearrange the equation and I can solve for an N2. And I would do that by doing the same on the other side. C2 times V2 equals N2. Well, there's some property linking both of these solutions. The solution that I started with, I dumped into the second one and I filled it with water, and something is going to be the same in both of those solutions. What's the common feature of my solution before and my solution after? What's going to be the thing that's the same that was in this solution and is now in the next solution? Sean? It would be the number of moles. Because I haven't added or changed any moles, I've just diluted it. So the way we figure how to solve these problems is we're going to use the fact that N2 equals N1, and that means C2V2 equals C1V1. But we always start with the 1, so I'm going to flip it around as I write it in the last time. C1V1 equals C2V2. And that is what we call our dilution equation. That's one of those things that is important enough, I'm going to put a box around it. Oh, a really shaky box. All right? Now, this particular equation is a ratio of concentrations and volumes. Even though we use the equation for molarity to figure this equation out, it's not that it's not that important for the not right now, Mark. A little later on, okay? It's not that important that we deal with molarity and liters. Because it's a ratio, the units will cancel out. So this particular equation, the C's can be any concentration unit. So it works for any concentration unit, any concentration unit. You can have percents in there, you can have molarity in there, you could have parts per million in there. All that matters is that they're the same, that the C1 unit is the same as the C2 unit. And that's going to be true, same for the volume. The volume can be any volume unit. As long as it's the same, you can work in milliliters or liters. You could even work in cubic centimeters if you wanted to, as long as their units are the same. And that's because it's a ratio. The same units on the left as the right, and the units always cancel out. All right, let's go ahead and solve some problems. Yep, beautiful. So we'll do a couple of examples. As you're writing that down, I'm handing you out a little practice sheet that has some extra dilution questions on them. Questions 8 and 9 on this page are a little more advanced, and because you guys are a little slow, we don't have to do them. No, I'm kidding. You're not slow. I'm running out of time. You guys didn't even budge on that one. It's no fun. If you wanted a little challenge and you wanted to think about 8 and 9, by all means you could do it. It's not something that I put on a test in this course unless I officially teach it, and I'm not, because we're just not going to get to it. But it is something that you will come across in the grade 12 course. We will have to do calculations like this, but it's not a big deal if we don't do it right now. I'll reintroduce it then. So 8 and 9 you don't have to do. All right. This stuff is simple stuff. All we have to do is make sure we've got our 1s together and our 2s together. What volume of concentrated HCl, 12 molar? They're the first things I'm encountering in the question. So what volume? That's the first one. That's what I'm looking for. So I might as well say V1 equals question mark, because it's the first V I encountered. And I don't want you to get hung up on whether 1 means before and 2 means after, because it really doesn't matter. What's the concentration of this particular what volume that I'm looking for? In other words, what's the number that I'm putting in for C1? 12 molar, because that's what I'm looking for. 12 molarity is needed to make 1.5 liters, V2, 1.5 liters, and the concentration for that is 0.100 molar. As long as the units are the same, molarity, that's fine. I'm going to stay with liters. That means my other volume will be in liters. So I just set it up and I go V1, C1, C1, V1 equals C2, V2, but I got it switched around, doesn't matter. C2, V2. So V1 is what I'm looking for. So I'll just leave that in there. 12 molar. C2, 0.100 molar. V2, 1.5 liters. I'm going to divide both sides, horrendous horizontal lines. Oh, not bad. Divide both sides by that 12 molar. Yeah, horizontal line. Whoa, exciting stuff. 12 molar. 12 molar. You'll notice that whole thing cancels that. That's the division. My molarity cancels my molarity. And so the only unit I'm left with, liters. And that's what defines my V1. And anybody have that number? Yep. Jess, what do you got? 0.125 liters needed. Or how many milliliters would that be? 125. 125 milliliters. You're right, 2 significant digits. So we should go to 0.13 liters. Yep. So I'd have to measure that out in order to make that. Okay? Pretty straightforward stuff, the dilution equation. All you got to do is pick out the pairs of information and away you go. As long as you've got them in the right pair, you just have to rearrange it in the equation and go. So again, don't be stressed out about what the 1s and the 2s stand for. You could have the 1 stand for the first one you encounter in the question, as long as you've paired them. What volume of sodium hydroxide solution can be prepared from 10 milliliters of 6 molar solution? So what volume, 0.5 molar? They're the things that are going together. So again, V1, question mark. This is the exact same question. well, with different numbers, but the same type question. C1, 0.500 molar. V2, 10 milliliters. C2, 6 molar. I guess the difference here is we wanted to find the concentrated one. Now we're finding the weak one. Now we're going kind of in reverse. We have the concentrated information, and we're finding the volume of the weak one. But numerically, pairing it up, it's an identical problem, right? It's just looking at it from the other way. So C1V1 equals C2V2, 0.500 molar. V1 is what we're looking for, 6.00 molar, and 10 milliliters. And I don't need to change that, because as I divide off that 0.5, bring it down underneath here, I'm going to have milliliters only left. And I'm not going to rewrite that with the line underneath it. Somebody just give me the answer here. Yep. 120 milliliters. And did you already round to 3 significant digits, or that's 3 significant digits? Excellent. Yep. Could be written as 1.20 times 10 to the 2, but that's okay. This is good. All right? Okay. Next. This one's a little different, and I'm asking you for a concentration. We haven't done that yet, but mathematically it's identical. And also notice I have one unit in milliliters and the other unit in liters. And that's the only restriction when using this equation. Doesn't matter what units you use, but they have to be the same units so they can cancel away. So again, when gathering your information, these are the first two that I'm encountering. So V1, I'll just write it as 15 milliliters. And C1 is 18 molar. And V2 is 1.75 liters, which is unacceptable. So we'll go back and fix it in a moment. And what's the new concentration? C2 equals question mark. And that's because it was second, the one I encountered second. Which one do you want to switch, the liters or the milliliters? Switch the liters to milliliters? Okay. So how many milliliters is that? 1,750 milliliters. Now we're ready to go. We've got it in the same units. C1V1 equals C2V2. C1 18 molar. V1 15 milliliters. C2 is the unknown, so we'll just leave it in there. And V2 is 1750 milliliters. So C2, I'm going to divide off the 1750 from both sides, right? I'm going to move it underneath here to figure out what that answer is, and you guys are good at that, so I'm going to just wait for an answer on C2. Jess? 154 molar, and I guess I've only got 2 significant digits in here, so 0.15 molar is the final concentration. So dilution equation is nice and easy. Okay, deriving it is easy, right? We took the concentration equation and we rearranged it, and we found the number of moles. That's C times V, and we just put the two of them together. All right. I do have a last example, but we're not going to do it. That's the one that's like numbers 9 and 10, but we're running out of time, and it's not a big deal. I can always introduce that to you next year when you need it. So there are homework questions out of the textbook. You have the worksheet, some extra practice, and that completes the lesson on making solutions. Again, I'll go over some of the videos a little later on in the week when we get some time to show you how this equipment works.